All right, let's get started. Welcome to the 7th lecture of topics in reinforcement learning. In the preceding 2 lectures, we have focused on deterministic, finite horizon, optimal control problems, and we have introduced some specialized form of method for approximation in value space. And we have primarily focused on rollout algorithms and touched upon various topics, including how to compute a cost function that in the presence of various constraints and so on. We have also mentioned multi-agent rollout as an approach to deal with large control space, which is the primary focus of this lecture. Here is the outline of this lecture. We will first give a brief review of approximation in value space, particularly rollout, and then through this review, we will bring up the focal point of this lecture, which is how to solve the minimization problem efficiently in face of real-time constraints. Then we will go through 2 examples to demonstrate how this minimization problem can be solved. The first one is the multi-agent rollout for warehouse robots pathfinding. We will again discuss the multi-agent rollout algorithm, but also focusing on the idea of changing the order in which the agents are optimized. We will show that through random reshuffling of the order, you can get performance improvement as a heuristic approach. Then we will look at another important problem, which is a multi-object tracking problem, also connected with the data association problem, whereby the goal is to associate objects over time, over different layers or frames. And in general, this is a very challenging combinatorial problem from mathematical point of view. And we will show that how the rollout ideas can be brought to bear to solve this problem. Okay. You have seen this picture many times. This is a deterministic finite horizon optimal control problem where the state evolve over time under the influence of control. And at each stage, we have a cost occurred under after applying UK, and this cost is accumulated over a finite number of stages denoted by N. And our goal is to minimize this finite cost associated with a particular trajectory by choosing appropriate control sequence. So for this problem, if the state and control are discrete, then it can be fully specified by a discrete graph with different layers, and each layer associated with all the states, and the arcs of the graph represents the control. And to solve this problem, and beyond this discrete case, it's possible, a principal approach is dynamic programming algorithm, which involve 2 phases. The first phase is going backward in time by computing the xk tail subproblems for all xk and all k. And by necessity, this is done offline and involve a lot of computations. So for each k, we solve all the xk associated tail subproblem and move backward to k minus 1 and so on, all the way go to the stage 0, at which point, if we get j0 star x0, then that is the optimal cost. And after obtaining that, we go forward to construct the optimal control sequence u0 star until u n minus 1 star. And this is the online play process, whereby start from an initial state x0. We perform this one-step look-ahead minimization calculation to compute u0 star. And that brings us to the next state, x1 star. And sequentially, we going forward for k equal to 1 till n minus 1. We compute uk star by this formula and get to the next stage and so on. As you can see, the distinguishing factor here is that for the offline training and backward calculation process, we need to solve all tail subproblems for all k. And that means if there are many xk in each layer, then we need to compute the same amount of jk star. On the other hand, for this going forward online play process, we only need to compute this formula n times. For each stage, we encounter one xk star, starting with x0 star. We compute its associated cost function, associated Bellman's equation minimization to get the minimizing control. And that's sufficient. So that means this formula need to be computed n time. It has nothing to do with the size of the state space. And that's it. So this suggests if we cannot compute J star exactly, it is still possible to take advantage of this going forward an online play procedure. And this is approximation in value space with one step look ahead, whereby we replace J star with an approximation J tilde during online play. So it's the same formula, except that the J1 star is replaced by J1 tilde. And suppose that J1 tilde in shape is somewhat similar to J star, then we hope that this U0 tilde can be suboptimal. And after computing U0 tilde, that brings us to X1 tilde. And sequentially, we go forward and compute UK tilde by similar formulas and get to the next stage and so on. So this is the overall picture of one step look ahead. Compare with the stochastic problem. Remember, in stochastic problem, one step look ahead, we have three challenges. So here, for deterministic problem, we have two challenges. One is how to compute the cost function approximation, this cost to go approximation, J tilde. And the other one is how to address this minimization problem in real time, because this is online play, which means this control need to be computed with some time restriction. In general, the variety of online play algorithms can be considered as a special case of truncated rollout with one step look ahead. So if we look at this picture, starting from xk, if we do truncated rollout with one step look ahead, we enumerate all the possible next state xk plus 1 corresponding to different control. And starting from there, suppose that we have some base policy pi. We run for a number of stages, let's say m, and then plug into the terminal cost approximation, which we denote by j hat. Then compared against the previous figure of one step look ahead, effectively, the J tilde used in this one step look ahead scheme will be the running cost, the stage cost, summed up under the base policy, and then plugging into the terminal cost J hat beyond the truncated horizon, right? So this will be the effective J tilde. And when no rollout is involved, the terminal cost approximation J hat here is the J tilde in the one step look ahead. When there is no truncation, which means if we run rollout all the way till the end of the problem definition n, stage n, so essentially starting from k plus 1, we go all the way running the simulation until n, then this term add up all the way till gn xn, then this is precisely the cost function of the base policy. then we are using the J pi, the cost function, as the terminal cost approximation. So this is the exact rollout. However, the problem that we mentioned earlier about this minimization still remains, which means suppose that here we have the possible next state, the number of possible next state are gigantic. Then how you can run the simulation, all of those simulation effectively, it may not be possible anymore because the sheer number of possible next stage is just next states are just gigantic. Then how do you deal with that? And that brings us to the focal point of this lecture, which is how to solve the minimization in approximation in value space efficiently. In particular, we will focus on two contexts. One is multi-agent coordination or multi-robot pathfinding type of problem, where the number of possible control is quite large due to there are so many different agents, and each one of them have their a fixed number of control to select from, and then it can grow exponentially quite quickly. And the other case is the multi-object tracking problem. Suppose here is a same vehicle on the road, and I just show the vehicle's position over different time instances. And in such a context, suppose you have a steady string of images coming from video. You want to recognize or associate or connect the same, attach the same ID to the same vehicle in order to construct a path of this object traverse over time, right? And this is the multi-object tracking problem. And our approach for the multi-agent coordination problem will be leveraging the problem structure by unfolding it to be an equivalent problem, and which will yield a legitimate Newton step. For the other case, we will show that by using the problem structure, we can purposely design this J tilde such that the remaining minimization problem become a standard optimization problem that can be solved routinely, very quickly. So this is terminal cost approximation J tilde can be suitably designed to enhance the minimization calculation. In other words, when you are designing this terminal cost approximation, you should also, in some cases, you should also bear in mind whether or not you make your own life easier when solving this cross-bounding minimization problem, because it is not the end that getting this J tilde. At the end of the day, you still need to compute the control. And to compute the control, you don't want to make your life harder by introducing a J tilde, which make this minimization problem difficult. Okay, at this point, is there any question? All right, let's get to the next part, which is multi-agent rollout for warehouse robots path planning. Again, we start with a review of this classical information pattern picture that you have seen multiple times. And the defining character is that despite being the presence of multiple control component or multiple agents, all the information collected by individual agents are shared with all the other agents. And the state information, as a result, the state information is shared. So when you select the control component, different control component, every control component selection is based on the common shared information. As a result, it is possible, suitable to define the problem within the framework of dynamic programming that involve the state X. The state X is the shared information by all the agents and the control U. And the control U here is composed of multiple components, and each component corresponds to the control of a particular agent. As mentioned in the preceding lecture, the agent is just a metaphor, and the important thing is this control structure. So for this particular case, if we have a policy, which we denote by pi, and for each stage, it have a function mu 0, mu 1, and so on, then the functions for each stage, based on the common information, need to select the component, each component. As a result, this policy can be represented in this form. So based on the common information X, it select mu k1. It can be viewed as decoupled as M functions. Mu k1 that decide the first component, mu k2 that decide the second component, and so on. And the last component is mu km. Therefore, you can conceptually, you can think this mu k1 is a policy this agent 1 is using, and mu k2 is a policy that the second agent is using, and so on. And the important thing is that all of them share the same information, which is X. At the same time, they are coupled in the sense that they could be coupled in the sense that the whole thing collectively should satisfy the control constraint, right? So those two are the characters you should bear in mind. Okay, so for this multi-agent problem, let's consider the standard or truncated rollout for this multi-agent problem. Here is the figure for rollout, exact rollout method using a base policy. Remember that in the preceding lecture, we have mainly talked about base heuristic, right? Base heuristic, it can be two types. One is sequentially consistent and one is sequentially improving. Here in this lecture, we mainly focus on policies, although it can extend to heuristic as well. But let's focus on policy, and policy are the ones that are sequentially consistent. So given the current state xk, what we do with rollout with one step look ahead is we enumerate all the control, and then starting from all the possible next state, run the base policy, and the cost associated with this number will be the Q factor of xk and uk. And similarly, the cost associated with this trajectory is the Q factor of xk and uk prime, right? So we calculate, in this case, 3 Q factors and compare their values and find one that attains the minimum and use that control. And suppose this is the smallest, so we choose that one. All right. Now, try to use this rollout methodology to multi-agent problem. You will find out that you hit a wall quite quickly for even small number of agents. So suppose for simplicity, let us consider that the control constraints has this Cartesian product structure. Essentially, this means that given the current xk as stage uk, each agent can choose its control independently within this control constraint set, right? So for the first agent, regardless of what control is select, it does not impact the feasibility of other control selected by other agents, right? So that means agent one can choose its control within the set freely and does not impact the feasibility of control selection of the second agent. On the other hand, this need not to be true in reality, and what we're going to talk about later on applies fully to more general case, whereby agent one selects some control may lead agent two have nothing to choose from. That's possible. Or agent one to select some control and lead the remaining agents not feasible to choose any control. That's entirely feasible, possible. So with that being said, let's consider this simple case where it admits this Cartesian product structure. Now, when applying standard rollout for the multi-agent problem with this control constraint set, at each stage, at state xk, remember we consider all possible controls, right? That means we're going to run this minimization for every component is select from this set UK1, the first component, for second component UK2, and so on. And as you may imagine, this can be quite large with even a modest number of m. Not to mention that in the context of rollout, this Q number is not readily available. You need to run simulation with base policy all the way till the end in the exact rollout to get this Q factor. Even without considering this simulation, the sheer number of control can be gigantic, which renders major difficulty or make this approach completely infeasible. So the remedy we have discussed earlier is multi-agent rollout, whereby we consider one agent at a time. It requires much less computation. So to this end, we consider this equivalently formulated problem where the control is unfolded. So here we consider a new system starting at X. For simplicity, I dropped the subscript K here. So starting from some X, after applying U1, suppose this order 1, 2, 3, 4, 5, M is by default given. So we are fixed with some order. So starting at X, we apply U1 and get to a new state, which is a pair X and U1, and at no cost. So here is no cost. The dynamic is from X and U1 and get to this pair X U1, and then apply at this state U2, which give us at no cost and give us this triplet X U1 U2 and so on, all the way to this point, which is an M tuple X U1 U2 U M minus 1. And at this point, after select control UM, we use the original system dynamics to get to the next state, X bar, at a cost X and U, right? And so only this stage has cost. So when apply standard rollout for this reformulated problem, we get multi-agent rollout, whereby at xk, it solves sequentially m minimization problems. So at this point, it evaluate the Q factors corresponding to all UK1 within the constraint set UK1, whereas all the subsequent control components are selected or fixed at the by the base policy control. And by doing so, we can find a control that minimizes all those Q factors with all the subsequent ones fixed at the base policy and optimize the first component. That brings us from here to a state here. And then at this point, to select U2, what we do is we fix U1 at the one selected in the first step, because this is the state we get, right? So it's xk uk1 tilde. This is the state. And at this state, we select uk2, whereas the subsequent ones are fixed by the base policy, right? So here is the state at this point, and we select control U2, again, from this control component set, not the entire product, but only feasible UK2, and the remaining ones fixed at the base policy. So after M-1 minimization problems completed, we get to this state, which is, oh, here is the typo. There should be xk as well. So it will be xk, uk1, uk2, all the way to uk tilde M-1. So that's the state here. And at this point, oh, here is the typo as well, sorry. Here should be M. So select M to get to the next state. And in total, it's M sequentially solving M minimization problems. And each minimization problem involving computing the number of control component numbers, not the entire product. Yes?
Each stage a coordinating factor in terms of a multi-agent coordination.
Well, in the multi-agent coordination, yeah, you can interpret that way, but it will be clear basically in the particular example. It's actually, if you have done the spider and fly exercise, then the control for this one will be a particular spider's move, right? And in the exercise problem, we have made life easier for you. So the control constraint set is follow this product term form, right? Following this form where a control selected by one agent is not affecting the other agent. But in more general case, let's say we require that two spiders cannot occupy the same grid, then the control is not independent anymore, right? They're going to be coupled. And still, however, the number can grow gigantic with the number of agents. And for those of you who are interested, you can test out if you add this new additional restriction that agent cannot collide with, or present multiple spider cannot be present in the same grid, then when computing, after computing the first agent U tilde, it's not anymore all the actions or all the controls of the second agent can be considered without considering the first agent. So without considering the first spider, but still the same line of minimization calculation goes through. As you can see, in the preceding formulation, when applying standard rollout, suppose that at each control component set, this set, we have n control, then the number of control need to be considered in this one step loop head is n to the power m. On the other hand, with this sequence of minimization calculation, at each stage, we consider n Q factors, perform minimization calculation, and move on to the next one, and so on. In total, the Q factors we need to consider is n times m, a dramatic reduction. Moreover, another important, theoretically important point is that given that multi-agent rollout is standard rollout applied to this problem, it is still a legitimate Newton step, which means we can expect the performance computed by multi-agent rollout is much better than the performance of base policy because it's a legitimate Newton step. As you have probably seen in your homework, you tested multi-agent rollout with standard rollout. And in terms of performance, there's not so much performance degradation from multi-agent rollout, right? In fact, in some cases, they are identical. The number of time it took is identical. So that's the important significance of this unfolding, state space unfolding, and that give us confidence why multi-agent rollout is a good idea. Okay, it seems I'm running quite fast today. The second half going to be a little bit heavier because we're going to get to the examples, and this part is pretty much review. So let's take 15 minutes break and get back with the examples. Oh, before I stop here, any questions? No?
If we introduce stochasticity in the environment, like if the system is stochastic, will this multi-agent rollout work in that?
It still works because at this point we have mainly considered deterministic problem and finite horizon and so on. So we have restricted our attention to deterministic problem. But all the ideas, everything here, the calculation goes through. However, of course, because it's a stochastic, that means every Q factor cannot be computed by one trajectory. Well, you can, but you're going to have a lot of variance, or you need to run Monte Carlo simulation to average the numbers over. And in fact, the same idea also applies to infinite horizon problem. But for infinite horizon problem, you have this balance between how many number of steps you're going to run simulation before you truncate, because you cannot run infinite number, right? So you need to truncate at some point, and where to truncate, and whether or not to plug into some cost function approximation and so on. And this is a matter of practical testing. And the other thing is how many number of samples given the number of rollout truncation horizon you are using. Because in the case of stochastic problem, again, the longer horizon you use with the simulation, the more stochastic random noise you introduce, which means if you want to have relatively small variance, you need to run more simulation and so on. So it's from practical point of view, our testing, typically we have found the truncated horizon 10, 20, and things like that is good enough. It's not really a good idea to run all the way till the end of like very, very long. For finite horizon problem, on the other hand, when the cost is primarily concentrated in the end, like only appear in the terminal cost and so on, then things get a lot more trickier because to start with, you cannot truncate without any terminal cost approximation, because suppose that you have a finite horizon problem where the cost only appear in the final stage. If you truncate after some number of stages and your terminal cost is 0, that means you run a bunch of simulation and each one of them have cost 0. So it gives you nothing, right? You need to plug in a terminal cost approximation. And that relies on terminal cost approximation. The accuracy of terminal cost approximation become more important, and longer horizon, like this rollout truncated horizon, become more important. So from case to case, it depends.
Like what kind of methods are used to estimate this terminal cost approximation?
Terminal cost approximation. Yeah, that's basically an art of its own right. So in later lecture, we're going to introduce through another application, we're going to introduce a methodology that basically reduce the state space. Suppose that you have a gigantic state space, you reduce and aggregate the states to a fewer number of states, and which can be constructed by using features and so on, and focusing on the smaller scale optimal control problem and solve it, and use that cost function of the smaller problem to represent this terminal cost approximation. There are other possibilities like problem approximation and getting data and training your network and so on, but that's
That won't
not
be applicable like for online.
No, the entire process will be an offline process, right? And once you have that, in the online process, you're going to rely on this offline trained or offline computed result for your control selection.
But like for the like approximate, like won't it depend on the data, like how you approximate that function? But like maybe like when you are updating the policy online, you might encounter different trajectories along.
Well,
which
that's
might not be that function trained or.
That's exactly entirely possible. And in fact, the whole point is to have a cost function approximation that approximate J star, not compute the J star. I mean, if we have a gigantic state space, it's never possible to enumerate all states and ensure that in your training data or in the represented states used in the aggregation is exactly covering everything you're going to encounter online. So at the end of the day, this is a approximate solution for problems that is infeasible for if you want to compute the optimal solution, right? Yes.
In the textbook, it was said that this multi-agent rollout and ordinary rollout are equivalent problems because all policies can be obtained in both the approaches. But I was wondering where, in case of multi-agent rollout, after suppose I select U1, for selecting U1, I'm just going to explore the trajectories with base policy for U2 and so. Yeah, how exactly are both of these problems similar or equivalent?
By equivalent, if you mean that standard rollout applied to this unfolded problem is multi-agent rollout, then I agree. So standard rollout, remember, standard rollout means that at a state, you select all control and run base heuristic, right? So if we consider standard rollout applied to this unfolded state space formulation, then we get this multi-agent rollout algorithm. But it's not equivalent to standard rollout applied to the original problem. Because again, if you consider standard rollout applied to this problem, to get a complete control sequence UK, U tilde K1, K2, and Km, you run M minimization problems, enumerating N times M Q factors, whereas the standard rollout applied to the standard original problem, you enumerate N times M, right? So that's not the same thing. Okay, any other questions?
But like if we assume if we are updating the rollout policy for a particular agent, and we assume other agent is gonna follow the base policy, will it count as standard rollout?
For this problem, again, for this problem, it counts as standard rollout. If you consider this unfolded problem, then it's standard rollout. But if you mean by account, you mean the original problem, then of course it's not standard rollout. Standard rollout consider all the combinations of all the control components simultaneously. In this case, we consider different control components sequentially.
Like if I assume like for the like one step look ahead, I would assume the agent one would do the one step look ahead, but other agent will follow the base policy from t equals to 0 itself.
I don't follow.
So it's kind of formulating in the same sense, but instead of like while calculating the control for agent 2, instead of considering the mu k tilde 1, we assume mu k tilde 1 is also calculated by the base policy.
Oh, you mean when doing this?
Doing update this, yeah. I assume like it also comes
So-
from the base. Then
I don't think it has something to do with rollout anymore. If simultaneously, let's say the first agent compute its minimization and all the others stick to the base policy, and the second one also do the same thing, all the others stick to the base policy and so on. And you can parallelize, yeah, that's true. But when you assemble them together, as I said, we have deal with the simple case where this is a Cartesian product, right? If it's not Cartesian product, it may not be feasible in the first place. On the other hand, even in this Cartesian product case, if you assemble everything together, you may get something that is even larger than base policy, because when you minimizing the first component, you are assuming all the others follow base policy. And similarly, when you optimize the second agent, you are assuming all the others follow base policy. So give you an example. Suppose that two cars are look like driving towards each other. And the first car, suppose that the second car gonna go straight, therefore, or it gonna make a turn, therefore it goes straight. And the second car also use the base policy of the other car and think they're gonna make a turn and go straight and collide into each other. And you have a much larger cost than so this kind of thing can happen because if you run simultaneously, then you lack coordination. The method lacks coordination that is essential or the major benefit of multi-agent rollout. And in fact, this is precisely why you need to solve those minimization problems sequentially, because the information of the first agent of calculating this UK tilde gonna be useful in helping the second agent choose its control. So therefore bringing this coordination effect.
But yeah, I got your point. Like if all the other agents would have followed the base policy, it might collide in the case of the example. But like once it like will it be feasible? Let's assume like if I have like 1,000 or like 10,000 agent, if my 10,000 agent has to wait for other agents to finish its update and
Well,
then it decides what to do.
Well, I have to say that all methodology have its scope of applicability, right? And if we are talking about 10,000, probably it doesn't make sense to formulate the problem exactly as the way it is. For example, if you want to, let's say if you run a big company with 10,000 employees and you are the CEO, then it makes no sense to, to precisely order each one of the employee what to do today, right? So it always have its scope of usage. And if you have 10,000 agents, then probably you need to partition into different groups and run coordination within each group individually, right? Okay. Yes.
So the standard rollout and the multi-agent rollout have similar performance, like empirical.
Empirically, yes.
Is there any way that we can prove that?
Well, not, not that I'm aware of. What we can prove is kind of low-hanging fruit. Essentially say that if you run this M minimization problem sequentially, in the end, you get some, suppose that the last UK tilde M attains the minimum. Let's say this minimizing number, this Q factor have some value, right? And if you go carefully with the proof of rollout, you will see that the cost function of multi-agent rollout is upper bounded. It's no more than this smallest Q factor calculated in the last step. And then if you look at the rollout performance improvement proof, you can see that the standard rollout cost is also smaller, no more than the minimizing Q factor in the rollout calculation. What we can say is that the smallest Q factor calculated in multi-agent rollout is guaranteed to be no smaller, typically larger than the minimizing Q factor calculated by standard rollout. That's the only thing we can say in general. But essentially, that is to say, for multi-agent rollout, after this M sequentially solving this M minimization problem, for the last minimization problem, we get some minimum number, right? Where this UK tilde M attains. And this minimizing number, minimum number, is an upper bound of the cost function of the attained multi-agent rollout policy. And this upper bound is larger or equal to the upper bound computed by the standard rollout that consider all the possible combinations of this U1, U2, and UM. But this upper bound, the relative difference of upper bound does not imply the actual cost, the difference of actual cost. So both are upper bound and the corresponding costs are smaller than those upper bounds. But in terms of the difference, the relative relation between the difference of the policy, which one is larger, that's a different story, and we don't know.
Is there anything that we can say about the gap between the upper bound?
From qualitative point of view, of course, yes, because it's Newton step, and you look at how this Bellman curve looks like. It's flat, and since its cost function is on the other side, which is flat, and you run Newton step, you get much larger improvement, right? And that's the only thing. And typically we see this gap from the base policy to the rollout policy is large. When it's a bad policy, after running one step ahead and rollout, you get much better result. And in fact, this is true not only in linear quadratic problem and in the multi-agent problem, also in larger scale POM-DP problem that we will cover later on. But other than that, there's not much we can say. Yeah. But there are a lot of practical evidence which shows the multi-agent rollout is just as effective.
Multi-agent rollout, it's standard rollout, represent Newton steps. If we are within the region of convergence of Newton's method, they are roughly the same. They both converge very fast to the optimal solution. If you're far away from the region of convergence, one may work better than the other, and reverse. But it's all luck of the draw. Newton's method, there are no guarantees that relate proximity of the current iterate to the solution and performance of the Newton step. In other words, in one direction, the Newton step may work very effectively and converge from far away, but in another direction, if the starting point is another direction from the optimum, then it may not work so well. It all depends on third derivatives, quote unquote, of the function that you're considering. And that's unpredictable in the context of rollout. So you can't predict anything about the relative performance of multi-agent and standard rollout. They are both Newton steps, and sometimes one works very well and the other one may not work so well. The reverse can also happen. Or the typical case is that both of them work comparably and extremely well. So any kind of theory that relates the two has to revert to Newton's method, and Newton's method is notoriously opaque and mysterious in its behavior. If you look for a theoretical result to publish a paper in this area, probably must not be able.
Is there any example like on which you can show like the standard rollout works well and multi-agent rollout doesn't work? Or maybe like goes to suboptimal, or like standard rollout goes to optimal.
I guess you can come up with some cooked example with a particular order that gonna mess up, as I will show in the second half of the of the lecture, that for this multi-agent path finding problem, if you start with a very bad order, and if you stick to this order, then multi-agent rollout definitely perform worse than standard rollout. But again, that's kind of academic rare case.
Basically, different orders represent different Newton steps. And so you pick one order and it represents a good starting point for Newton's method. You pick a different order, takes a different starting point. But the starting point, the effect of the starting point is unpredictable. And you have, it's a matter of using heuristics to identify a good starting order. Of course, intuition can also help you here, but intuition is not safe and guaranteed to give you good results.
All right. So let's start with 15 minutes break. All right, so let's get to the second half of the lecture. And now we're gonna focusing on some applications. As the first application, we talk about multi-agent path finding problem, whereby we have multiple warehouse robots moving around, sharing the same physical space to pick up some goods in the warehouse and deliver to a targeted location. Unlike the spider and fly example, you have tried in your exercise, you may imagine that two warehouse robots cannot share the same physical space, right? So the target here is the control constraint set is not anymore decoupled, although in what follows from modeling point of view, we're gonna consider it to be decoupled. So in this particular figure, we have three agents, and they can communicate with each other, sharing their view, so that all of them sharing the same information and sharing their decision where to move as well. They can move in 4 different directions and stay still at the current position with perfect vision. So if we model this problem, we can use, in this particular case, we use a grid representation, whereby each solid circle represents one agent, and each agent has been assigned to some target, and that is encoded by the holy circle with the same color for example, this agent need to move to this particular position, and this agent need to move to this particular position, and this agent need to move this particular position. And the objective is to reach their respective targets in minimum time while avoiding collision with each other. So they are the same team. They are owned by the same company and work in the same warehouse. It's not a competition, so they work together. And a simple heuristic in this context could be that each agent follows the shortest path to the respective target, assuming all the other agents are not present. As shown in this figure, that means for this agent, it simply move to this direction and all the way upwards. It can reach its target in shortest time. And similarly for this one, move all the way to the left, and the blue one move all the way to the right and make a right turn. So, but of course, this is a fantasy here, assuming all the other agents are not present. And given that they share the same physical space, blindly follow the space heuristic can lead to collision. And also here, this solid black, we mean some obstacles, static obstacles. So having modeled the multi-agent path finding problem using this grid word representation, let's see how we can formulate the problem by using dynamic programming. Given that all the states, all the agents share the information with perfect vision, so we're not considering the case that this agent, its view is occluded, therefore it cannot see this agent and those kind of things. That would make the problem much more challenging. We're considering the case where all the agents are aware of their current location and they share the information with each other. So this agent is perfectly aware of all the other two agents' location, and when it makes its own decision, and it can inform all the other agents and so on. Therefore, the dynamic programming formulation allows us to applies to this case, and we can consider as state the current location of all the agents, as well as whether or not the target has been reached, right? So given the current case, it will be the locations of 3 agents, robots, and their respective target that yet to be reached. And the control, as mentioned earlier, each agent has at most 5 choices. Their combination can grow exponentially with M. Now, next is kind of a design choice, whether or not you want to encode this collision as hard constraint or make it part of the cost. And in the particular application, we have used it as a cost because that makes the simulation running much easier, but it's a design choice. And so the stage costs relate to the number of collisions and the number of reached target. So once you reach a target, you have a negative cost, which is incentivize you to reach a target and incentivize the robots to reach a target. And we design a big cost for collision. So hopefully I have convinced you that it's not a good idea to use standard rollout in this context, because roughly speaking, at each stage, using standard rollout, you need to deal with 5 to the power m approximate Q factors. So as I showed earlier, multi-agent rollout reduces it to the number of Q factor evaluation to 5 times m, while maintaining the good performance property. The key idea here is to break down the control into a sequence of one agent at a time moves. And at each stage, let's focus on this particular case as an example. Suppose this is agent 1, this is agent 2, and this is agent 3. Okay, let's focus on this case 2. It's more, here is more crowded, so it seems obvious that it's going to run into some collision. So if we focus on this case, suppose this is agent 1, agent 2, and agent 3, then at each stage, starting from this current position, it first minimizes the Q factor associated with first agent, whereas agent 2 and agent 3 follow the base heuristic. You try all 5 different moves of agent 1 and then use the base heuristic. Well, all agent 2 and 3 follow the base heuristic, which is illustrated by the arrows here. And you count how many number of steps it requires for 5 different moves, and also count how many collisions has occurred. And based on this cost, you find what is the best action for the first agent. And then you move on for the second agent, assuming that the current stage, agent 1 use the control selected in this phase, and agent 2 try 5 different moves, and agent 3 follow the base heuristic. Eventually, we move to the last agent, and the new ingredient that I will show shortly is that we allow a change of order in which the agents are selecting their control at each stage. Essentially, as the professor mentioned, this amounts to a different Newton step. And it could happen in particular cases, like in this case 3. You can see by following their base heuristic, agent 1 go all the way to here, agent 2 and 3 go all the way, so they share this corridor. And if they blindly follow their base heuristic, they're going to get into collision. But from our point of view, it's so obvious that this one, by moving downwards first, can avoid. And now suppose the calculation, the rollout calculation, the order is this one first, this one second, and this one third, then it may not be possible to avoid collision. Whereas if you try this one first, then in the first step, this agent gonna realize, okay, by making space and do this way, it can leave the free space for agent 2 and 3. So obviously here in this case, order matters. And that's what we're gonna show next. So now we look at the animations of all 3 cases, whereby the blue one is agent 1, and the red one is agent 2, and the green one is agent 3. So let's get started. Okay. So in the beginning, we're going to illustrate the trajectories of 3 agents following blindly the base heuristic, and we'll see how many costs will incur. There is a discount factor involved, 0.9. Okay. In this particular case, actually, following the base heuristic is good enough. There is no collision that ever occurred. But nonetheless, let's try multi-agent rollout. Remember, in multi-agent rollout, suppose that we fix this order 1, 2, 3. Agent 1 started from agent 1. So agent 1 at the current position, try all 5 different moves, going to the left, going down, and right, up, or stay still. You try all 5 different moves at the current stage, and the subsequent stage follow the base heuristic, base policy, which is the shortest path. to get to the target. So for agent 1, it runs 5 different simulations, use 5 times the base heuristic, whereas agent 2 and 3 blindly follow the base heuristic. Then we run all those simulations and find out which one have the smallest cost. So you can see, moving to the right, at the current stage for agent 1 has the lowest cost, which exactly is the move suggested by base policy. So therefore, we mark the selected move here by agent 1. Then for agent 2, you can see it has go to the left. It cannot go down here and go to the right, go up or stay still. Try 4 different moves and then construct the remaining trajectories following the base policy. And you can see for agent 1, it now follow the trajectory that's selected in the preceding calculation. In this particular case, the preceding calculation recovered the base policy, so there is no difference. But in subsequent simulation, you can see there is a difference. So the agent 1 follows the trajectory selected in the preceding calculation, and agent 3 blindly follow the base policy. And now at this point, you can see there are two costs that attains the minimum and equal. Typically in rollout, especially in discrete problem, it's quite possible that I would not say often, but it's possible that you're gonna encounter situations where there are multiple actions or controls that attain the same minimum. And in some cases, it doesn't matter that which one you choose, but in some cases, it can make a difference, as we will see later on in one of the applications. Nonetheless, it's a good idea that you stick to some rules regarding which one you attain as minimum. And typically, it's a good idea if your previous control has the base policy attain the minimum, then just stick to the base policy. So in this case, agent 2 realized that running the base policy is good enough, so stick to that one. Now we move on to agent 3. Again, for agent 3, similarly, it has 1, 2, 3, 4 feasible action, and going up is not feasible, and runs 4 times base heuristic or base policy, whereas the agent 1 and 2 choose the trajectory, stick to the trajectory computed in the earlier step. Now we run the simulation and we find stick to the base policy is good enough. So through all those calculations, we recover the base policy, which in this case is optimal. Let's move on to the next case. Now this one is more narrow. Like the situation is more challenging because all the agents share the same corridor if they follow their base heuristic or base policy. And you can see there is 2 collision or 3 at this point happened, and which leads to a large cost. Now, if we run multi-agent rollout for agent 1, it has 4 feasible actions. And just as in the preceding case, we construct base policy. We apply base policy for agent 1 after trying out all 4 different actions, and agent 2 and 3 stick to the trajectory given by the base policy. Now you can see the cost starting from 397 has reduced to 119, which means there is only one collision. And you can see the agent 1 has made an effort to try to avoid agent 2 and 3, right? So this is the first step. And for agent 2, we'll make try all 5 different moves. And you can see at this point, it already find feasible solution, right? Apparently, agent 2, by making a right move first, kind of leave space for agent 3. So that's the whole point. And now for agent 3, there are 3 feasible actions. And you can see in the preceding case, when following the base heuristic, agent 2 is in front of agent 3, I believe. And whereas in this case, now it falls behind and makes space for agent 3. So again, we recover the same cost function, which is optimal in this case, I think. And in this particular setting, this order has been enough, has find the optimal trajectory, which means this particular Newton step works in this case. Now let's look at the third case. And again, we follow the base heuristic because they share the same corridor, get into collision, it doesn't work. Now, following the same procedure, starting with agent 1 and run simulation, and we get something, we actually recover the base heuristic, still involve collision. And for agent 2, and in this particular case, it tried to make space, and in this case, it detoured from the original path. Those two seems promising. Let's see. Okay, it seems the collision has reduced, but there is still collision. Number of collisions reduced from 358 cost to 191. So let's get back to the last one. Now we get even smaller cost, here 150, but there is still collision, right? So after this particular rollout order, we did not get a satisfactory performance. So let's randomly reshuffle the order in which the agents are optimized. And in this particular case, as I mentioned earlier, start from the last agent. So for the last agent, you can see its feasible action is going to left, right, and down.
But like in the case when the agent order was 1, 2, you did only one look.
Yeah, one step look ahead. So I will get back there shortly. Let's finish the animation. So in this particular case, going up is not feasible, right? And we get to run the simulations. And as you can see, in this particular case, with even only with this particular one agent, you already find optimal path. So this is clearly demonstrate the order in which the agents are optimized matters and make a difference. In this particular case, show it make a big difference. To comment on, okay, I'm guessing what you are saying is that this is just one step look ahead. And if you continue with the with multi-agent rollout and following the same order, it may be possible upon when approaching the collision situation, they can avoid each other, right? That's actually true. So even stick to the original order by following the same, by using multi-agent rollout and upon close to each other, in this particular case, it's possible they can still avoid collision because at each step, their agents, the trajectories are updated for all the agents. So that's a good point, but I still want to emphasize that even in this toy example, it makes a difference by changing the order in which the agents optimize their actions. And in fact, in the I'm going to show shortly, in larger scale simulation and larger scale tests involving 200 agents, sometimes it's not possible anymore to stick to the same order because you can see collisions are imminent. You need to change order in which the agents are optimized. Yeah. All right. So as mentioned earlier, that changing order just amount to a different Newton step. It's still a Newton step, but different order, different Newton step. So it corresponds to a different reformulated problem. In this particular case where the orders are reversed, we are considering the case where starting with the X, after applying the control for the last agent, we consider this to be the new state, and then apply the control for the second to last agent, we consider this to be the state, and so on. And similar as in the previous case, there is no cost here, there is no cost here, there's no cost here, and so on, until at this point, after select the control for the second all the way to the end, all the other agents, we select the control for the first agent and move on to the next stage. Remember, all those things are happening in your mind or in the head. You are simulating all those things. It's not happening in reality. In reality, you start from here, all the control are selected at once, and you jump to here, right? And all those things are happening inside the computer, in simulation. And reshuffling the order of agents results in a different, yet still equivalent problem to the original problem. Therefore, the multi-agent rollout is still a Newton step, and multi-agent rollout allows parallel computation of Q factors. Okay, here I need to clarify some point that by parallel computation of Q factor, I mean the Q factors corresponds to different here. So in our previous case, each component have 5 control actions. So we can parallel 5 different Q factors in order to find this and then move on to this one and parallel all those 5 again, and move on to the next stage, parallel all those 5 again, right? We cannot parallel the Q factor of this one with the Q factors of this one. This need to be done sequentially, and that's very important. On the other hand, suppose you have many more computation nodes than 5. Let's say you have 20, not 20, 50. Let's say you have 50 nodes. Then it's possible you can pack those 2 components together and treat them as one control, right? Because considering all the combinations of 2 control requires 25 Q factor. Given that you have 50 computing nodes, you can run simultaneously all those 25 Q factor all at once and find out what is the minimum for all those 2. As a result, suppose we have M equal to 10. If you compute control for each agent once at a time, you need solve 10 minimization, Q factor minimization problem. But given that you have packed 2 components together, now you need to solve 5, sequentially 5 computation minimization problem. So that's a way to reduce the computation time. Another idea is multiple base heuristic can be applied to enhance the performance further, as we have, just wait a sec, as we discussed earlier that in the preceding lecture, we have this, if we have multiple heuristic, we can combine them together to have a super heuristic, and similar idea apply entirely in the multi-agent setting. And all of those are independent of each other and can be combined to further enhance the performance. And in the textbook, there is some additional material for order optimization and other variations. Please.
Combining two states, you will increase the number of transistors you're looking at.
Exactly. So suppose that for each U, you have 5 controls, right? And if you combine, simultaneously consider those 2 altogether, then at each step, you are considering 25. But I'm assuming that you have more computing nodes than 25. Then you can run all those Q factors altogether simultaneously, right? Okay, in practice, running many computing nodes simultaneously can be a practical challenge, but let's be just be a bit idealistic at this point. But in general, depending on how many computing nodes you have, you can design suitably whether or not to pack some of the control elements together or deal with them separately. Yes. No. At each in the implementation I gonna show shortly, you use a particular order and you do optimization, one agent at a time. If it works, you go to the next stage, but you need to keep track of what is the previous order in which you have optimized. And then you stick to that particular order as the starting point to do the optimization one agent at a time. If that does not work, you reshuffle the order. What you cannot do is you choose the order and optimize and it works and get to the next stage, you reshuffle to start with, and that may mess up the previous calculation, because the previous calculation managed to find something good for Newton's step. And if you immediately get to the next state, you immediately change the order in which they were optimized, then you can get into trouble. Yeah.
Can you pack more than 2 components?
Again, that depends on how many computing nodes you have in an effort to reduce the number of minimization problems you solve sequentially, right? Remember, for each component, you are solving a minimization problem by considering all Q factors corresponds to different or a control component. And after fixing this particular control component, you move on to the next one and so on. Suppose the order is fixed, you move on to the next one and so on. So in this particular case, we need to solve M problems sequentially. Now, if you pack 2 components together, consider them simultaneously, you need to solve M divided by 2 optimization problems sequentially. And therefore, it's going to reduce the computation time from the previous amount to half of it. But this is based on the assumption that all the Q factors can be evaluated simultaneously. So back to your question, whether or not I can pack more than 2. I mean, of course I can. Suppose that each component have 5 control element. Let's say I have 1,000 computing node. Then I can afford to pack 3 components altogether, because 3 is 5 to the power 3, which is the maximum amount of Q factor is 125. Given that I have 1,000 computing node, I can run simultaneously this 125 simulate 125 Q factors simultaneously, and once they were evaluated, I find out which one is the smallest, and then move on to the next stage and so on. So it depends on how many computing nodes you have. Okay? Yes. Yeah.
Under what circumstances you are not allowed to change the order?
It's not that you are not allowed to change the order. It's that once you find once your control is selected according to a particular order, you move on to the next stage, and then you run rollout again. You should stick to the same order to start and test out whether or not rollout gets something good. To clarify, given that you are at the current state xk, you run multi-agent rollout after using a particular order of agents, and you find a control, and given the xk and uk tilde, you move on to the next state, xk plus 1. And then at xk plus 1, you run multi-agent rollout again, right? But when you run this multi-agent rollout again, you should to start to try still the order in which uk tilde was found, not to change the order completely. If you use the same order and does not give you a very good result, you do reshuffle. So that's essentially is to provide some consistency of the improvement, because you can come up with example where you fix a particular order and you use multi-agent rollout and find a good control, you move on to the next stage. And then at that point, immediately you reverse the order. And you all of a sudden you find out nothing works by following this new order. Because in the previous case, you already using a particular order, you already find something good with that Newton step. Now, if you change the order completely, you may switch to a different Newton step that is bad. I think it will help you to understand this by looking at some small scale example involving 2 or 3 agents. You will see that like having a fixing an order and you get a good control and move on to the next stage. Immediately you switch to a different order and all of a sudden everything collapsed.
So the question is order dependent on the state or the stage that you are?
Yeah, of course. I mean, for different situation, then the order in which they are optimized, definitely. Yeah.
It happened at once.
It happened at once because it considers all situations. It considers all combinations. So again, there nothing is free, right? In the example I'm going to show shortly, we have 200 agents, and you're going to consider 5 to the power 200 Q factors. And if you manage to do that, then you don't need to worry about order. All at once, you consider all combination. Essentially, you cover all the cases, all the orders. But can you afford considering 5 to the power 200 Q factors? The answer is typically no. You don't have that many computing resources available. So then you need to resort to this multi-agent formulation and consider way less Q factors at the expense that some order may not work. That's why you need to change it once in a while. Okay? All right. So let's look at the problem that considered in this paper, where the base policy is, as I mentioned, the shortest path from the agent to the target by following, assuming all the other agents are not present. And given the character of the space policy. So suppose we are focusing on this particular agent and all the others are not available, are not here, not present. Then all the shortest paths to all the slot that you deliver the good and all the distance, all the passes from different shell to different dropping points. So here is the dropping points of the good. Some robot pick up some good from the shell and deliver to a dropping off point. And given the character of the base policy, it can be computed and offline and stored in a lookup table, which make the simulation can be run relatively fast. And another fact is that the rollout can apply to a changing environment. So in our testing, we tested the situation where some robot just break down in the middle way and doesn't work and block the road and so on. And rollout still works. And we tested up to 200 robots in simulation and required computation time way less than a second. And you can find the code here, and the paper is given here. Now, okay, unfortunately, this is a low resolution animation, but you can see this is run in real time. It's done in, I don't remember, it's in C or C++ code. And basically, the simulation environment is just a gigantic matrix. And in the grid environment, the each cell is represented by a component of that matrix, and the number of agent available in a particular cell is the number in that matrix. That can be run fairly fast. And since the base policy is stored as a lookup table, it can be accessed pretty quick as well. And 200 robots, essentially we are solving 200 problems sequentially. But given that the simulation is just updating some matrix over a few number of steps, a fixed number of horizon, and that can also be done fairly quickly. And the whole thing can be run fairly quickly, in which case we can afford to coordinate up to 200 robots. Okay, any question at this point? Let's move on to the next application, which is approximation in value space applied to multiple object tracking or data association problem. First, let's discuss the general discrete optimization problem. Some of you may feel this is familiar, and because this can be the traveling salesman problem that has you have tried and studied so hard, can be a special case of this general discrete optimization problem, whereby our goal is to minimize a cost function g of u subject to the constraint that u is belong to this constraint set u. We assume that each solution u has n components, u0 to un minus 1. Using the traveling salesman example as to mapping to this general discrete optimization problem, this will mean the city you visit first, and this is the city you visit second, and so on. And this set is composed of all the complete tours that is feasible for the multi-agent, for the traveling salesman problem. And to consider, and we can view the components as the controls of n stages. With this view, we can define a dynamic programming problem that we can address. That is, we consider a k-tuple, again with a fixed order, u0, uk minus 1, and with a fixed order, we consider the k-tuple as the state xk. And starting from artificial state S. So starting from this artificial state, we apply u0, and we get to a state which is composed of only U0. And then you apply U1 and get to a new state, which is the pair U0, U1, and so on. U3, you append it to the pair and you get the tuple, triple, and so on, all the way. After applying the last control, you get the complete U that should satisfy this constraint. And there is no cost in all those transitions except the terminal cost, G of U. So all the other costs are 0. And here is the terminal cost is G of U. Of course, this formulation typically make little sense for exact dynamic programming, because if we're going to run dynamic programming for this problem, what are we going to do? We start with the last stage and define Jn equal to this, essentially enumerating all the control, right? Enumerating all the U's. That's brute force. So it makes little sense, but often make a lot of sense for approximate dynamic programming and approximation in value space. As I mentioned, for the dynamic programming formulation, if we're going to solve this problem, we're going to start with this function, or the xn, the terminal cost, g of xn, set jn star equal to g, which is the cost of this problem. And then for all the remaining stages, we run the corresponding dynamic programming algorithm. Compare with the previous formula that we have seen here. Previously, there is a stage cost G, right? But this stage cost is missing because all the other stages has 0 cost. Also, in the previous case, we have this f of xk and uk, and that's missing as well because the new state is simply appending uk to the xk. You get the sequence of u0, u1 to uk. So this itself is the system dynamics, and the uk of xk need to be suitably defined such that the entire thing has a feasible solution, has a feasible U in the end. And we can then construct the optimal solution that is going forward, starting from the artificial state, and compute one component at a time using this formula. For this problem, the approximation in value space use some cost function J tilde in place of J star. And as in the previous case, starting from the artificial initial state, for all the remaining stages, we move forward and set a control to be the one that attains the minimum from this formula where J tilde is in place of J star. Now let's see how this can be applied to multi-object tracking problem. Now this is 3 images from a video from a civilian camera. After some initial algorithm, it recognized in each image there are 3 people. And our goal is to associate or attach the same person with the same ID. Essentially, it's aimed to match the same objects over various frames. And as you can see, if we abstract it in this way, here is the 3 objects in the first frame. Here is the 3 objects in the second frame, and here is objects in the third frame. Essentially, what we want to do is to find out those arcs that connects the same objects over different frames or different layers, as will call it shortly. And this problem is highly non-trivial because to start with, some objects can be occluded by others, and the object's appearance can change from frame to frame. On the other hand, it's also, it requires real-time computation because typically this civilian camera come in, the stream of images come in, and you would like to have this object tracking algorithm done in real time. For example, in the case of vehicle trajectory prediction, you want to have the vehicle trajectory built within a short period of time in order to predict how it's going to move at the next time instance. It's an important problem with many applications like traffic monitoring, robotics, consumer analytics, augmented and virtual realities. Yes, go ahead.
Two things. One. Yeah, here an xk is sequence of u0 to uk. Here defining
U0 to UK. Yeah, U0 to UK minus 1.
cost of u0 to like taking choosing uk in terms of uk plus 1 or
Oh, you are referring to this formula?
yeah, that
Okay, for this formula, it is a substitute of the optimal.
that formula I'm getting the intuition for like
So it's a dynamic programming calculation, right? So remember, in the dynamic programming calculation, you start backward in time and start as stage n and setting this function equal to the terminal cost, which in this case is g of xn, right? And then you run backward in time and using the dynamic programming formula. The standard dynamic programming formula here is minimize a sum of the stage cost and the optimal cost of future state, right? The stage cost g in this problem, the small g, is 0. So as we mentioned earlier, here, there is no cost. There is no cost until the terminal cost here. So we have no cost. Therefore, this g is missing. We don't need that, right? It's 0. And typically, also, in dynamic programming, this formula gonna be jk plus 1 star of fk, xk, and uk, right? And fk of xk and uk, in our case, is simply given the xk is this, the xk plus 1 is just pending the uk to the end. Therefore, it suffices to just write in this way, right? And then here, we just approximate this. Okay. Now let's look at the mathematical problem of this multi-object tracking problem. It can be modeled as multi-dimensional assignment problem where there are n plus 1 layers of nodes. So you can imagine this is different person in the preceding image stream. And each frame, of course, here we made some simplification that each frame has the same number of people. It's possible, or objects. It's possible that different frames gonna involve different number of objects and so on. But for the moment, let's just leave it as it is. A grouping consists of n plus 1 nodes. So there are n plus 1 layers, and a grouping consists of same amount of nodes as the number of layers, where each node in a grouping belongs to a different layer. And we denote IK as the node that belongs to the case layer. So in this case, this is a grouping. And using the multi-object tracking problem, this will be the person that move across the space in the different frames. For each grouping, there is an associated cost depending on the entire grouping. So the cost is associated with this entire grouping. And for example, again, using the multi-object tracking problem, it can be the one that represents similarity of the objects in different frames in a way to encode how good this grouping is. Our goal is to find M groupings so that each node belongs to one and only one grouping, and the sum of the cost of the groupings is minimized. In a way, we want to find the matching to make all the objects in different frames look similar, or to be the right one, judged by the ground truth. Now, how can we model it by the discrete optimization problem? Well, we can consider this, the matching between the first and second frame, to be U0. And after matching the time from the frames from time 0 to time k, the matching between the frame case frame and k+1's frame is the control UK. So this is the control, and the preceding matching is the state. In this particular case, we don't need to worry about the order in which different UK, because naturally images come in time, and you cannot matching the time frame in the future and then go back match the frame in the beginning. But of course, in a different setting, it may be a problem of its own right. So if we want to solve this problem, using approximation in value space involves a few different key ideas. One is one-step locale minimization. Okay, so what are the UKs here? The UKs, the feasible UKs, are all the combinations that match one object in case frame to a different objects in k+1's frame. So this is basically the purple line here together collectively is one feasible control, right? Another feasible control would be this one matched to this one, and this one matched to this one, this one matched to this one, and this one matched to this one. This is another feasible control. What is not a feasible control is all four objects matched to this one, and the remaining three left unmatched. That's not a feasible control, right? Naturally, this thing needs to be constructed on the fly, but in our case, it can be constructed at the same time pretty much when computing the minimization. And we run truncated rollout. Suppose that we have some rule of thumb, very simple ways that can match objects in the neighboring frames. We match them together, and we match a few frames into the future. And what we consider as cost function approximation is relying on the matches produced by the base heuristic. Suppose that we want to select UK, our base heuristic run truncated rollout for the future 2 frames, and our cost function for this control highlighted here relies on the future matchings together with this xk. Now at this point, the Q factor minimization, given that we have fixed the matching of the future, and the minimization of UK essentially involve solving a bipartite matching problem, a two-dimensional assignment problem. And within our context, we get a result that is robust and consistent matching against occlusion. And further details can be seen in this paper. Now let's give an animation of the exact rollout applied to multi-object tracking or multi-dimensional assignment, whereby we have 6 layers as shown in the previous case, and each grouping has a different cost. Suppose our base heuristic, base policy is simply to assign the same, objects of the same different layers by using this horizontal, almost arbitrary grouping methodology. And you can also use other ways. And then starting from that cost, you're going to see the cost steadily reduce. And in this particular case, you get optimal in the end. Okay. So this is the total cost of the base heuristic, which is 112 or 113. So what's going to happen is, given the base policy is this horizontal line, right? Then for every feasible grouping, for example, this arc, we want to associate the cost with this arc in order to solve this multi-object tracking problem for this frame. What we do is the arc cost of this particular arc, which is shown in this item, is in fact the cost of this grouping. So the cost of this arc is the cost of this grouping, and the remaining portion of the grouping is constructed by the base policy. And similarly, the cost of this arc is the cost of this grouping, and that is given here, right? 17. And similarly, all the matchings, all the arc cost can be constructed by relying on the remaining portions produced by the base policy. Therefore, we have a two-dimensional assignment problem that can be solved very efficiently. And starting from the base policy cost 112, we get a cost that is 86. So after updating this frame, we get a cost that is smaller than the cost of base policy. Then we repeat the procedure. At this layer, previously it's the horizontal assignment, right? Now we compute a cost matrix of between the layer 1 and layer 2, whereby, for example, the cost of this arc will be the cost of this grouping, and the cost of this arc is the cost of this grouping. So by relying on the tail portion constructed by the base policy, we construct J tilde for all the control UK here, U1 here, right? And that's given in this cost matrix. And then we can find the U1 that minimize the cost of all the J tildes so that it's still a feasible assignment. And this is a standard two-dimensional assignment problem. And you can repeat this procedure for this layer and for the next layer, and you can see the cost further reduced to 57 after 4 layers. And in the very end, in this particular case, we get the optimal assignment. So again, let me repeat, for at this layer, suppose at this layer, given that you have constructed the assignment of the preceding 3 layers, and the tail portion is given by the base heuristic, each arc between those 2 layers depends on the tail portion and the initial portion. So this arc's cost, or the J tilde, corresponds to this particular case is the cost of this grouping. And you can put them all together and minimize the UK here. Any question? Yes. Oh, in this particular case, since I'm just illustrating an idea, so the cost of all the groupings are randomly generated. In the multi-object tracking problem, the cost involve the similarity of the objects and some other stuff, but it's still a grouping cost. It's not completely decomposed. Let's say each arc has its own cost, and the grouping cost is the sum of the arc's cost. Then you don't need to do all those complicated stuff, because you can just solve this problem, minimize the cost of this arcs, the sums of this arc, and go to this one, and so on, because it's completely decoupled problem. In this case, the grouping cost is, the cost that depends on the complete grouping, not as sum of the arc cost. Then this problem is much harder. Okay. Now let's get to the application of multi-object tracking. In the base heuristic, it involves some Kalman filtering to predict how a human gonna move in the next time instance and so on, and using neural network and stuff like that. And let's focus on this gentleman, which is assigned with ID 17. Now it moves over time, and at this point, he is occluded by those people. And when he reemerge, it becomes 41, because this particular base heuristic only considers the next frame and only considers similarity of next frame. And given that this gentleman is lost in the video in the middle frame, then when he reemerge, he's assigned as a new person. Okay, now let's look at our methodology, whereby it starts with ID 16, and when he reemerge, it's still ID 16, because by looking into the future, it realized that in future, the same gentleman reemerged and was matched with this hidden trajectory. So to give you some practical details, of course, as the practical problem is not as clean as the mathematical problem I have described earlier. To start with, each frame may have different number of people, right? There are people emerge, and there are some people disappear or running out of the range of the camera. And there are some people also hidden or occluded by other people or objects. So what happened is, when a person or object is all of a sudden disappear, then the algorithm still assume the physical presence of these objects and keep it in the trajectory, imaginary trajectory, for a few future frames. And it was until after a fixed number of steps, this same object still missing, then it will completely discard. And in this case, given even he is temporarily occluded, there is still a hidden trajectory running, assuming this person is present, and when it reemerges, since it looks into the future using the base heuristic, he eventually is picked up. And therefore in the object tracking algorithm, you realize that at that point, there's no reason to assign a new ID to this person because this in fact is the same person. Okay, now that conclude our lecture today. And in the next lecture, we will cover a new application, which is computing the most likely sequence generated by n-gram. That is the model we use to model the large language models. And for the inference problem in hidden Markov model, we're going to show that the rollout algorithm can produce approximate solutions that works better than the greedy heuristic or random solution, which is used primarily in the inference algorithm for large language models, and demonstrate its application in large language models, but mostly transformers. Okay, thank you for your time.